Okay, so lecture 4, what we're going to cover here is a couple of more axial deformation topics, and we're also going to look briefly at stress concentration. So we'll start off with statically indeterminate axial loads. Okay, so let's say we have a situation like this, where we have a bar that is fixed between two supports like this, and a load is being applied F. And let's say that this is point A and this is point B. And what we want is simply we want to know what the stress in this object is due to load F, assuming that we have a magnitude for F and some dimensions. So that requires getting our internal forces, and we can see that we're going to need our support reactions. Okay, so let's go ahead and try and get our support reactions. Let's draw the free body diagram of the object. So we've got okay, load F being applied. There's our externally applied load, and we've got AY and BY. There we go. And this is ignoring body forces. The weight of the object itself. So some of the forces in the y direction has to be equal to 0, so that gives us what AY plus BY is equal to F. And if we had a magnitude for F, well, that would leave us with one equation and two unknowns, AY and BY, and no way to solve it. So this is a situation that's called statically indeterminate because it can't be determined, the support reactions can't be determined by the equations of statics alone. So does this mean we're stuck and we can't figure out what the support reactions are and we can't figure out what the stress in the object is? Well, no, because we can actually write one other equation that we know to be true with the knowledge that we've already learned in the first 3 lectures. So the other equation comes from axial deformations, and the axial deformation equation that we learned last lecture. So one thing we do know also about this object, as well as being static, so some of the forces in the y direction having to be equal to 0, is that if support A and support B are rigid, then the total length change of object AB when load F is applied has to be equal to 0. So we've got delta LAB is equal to 0. And this is one of these cases where we have to apply superposition, so that would be point C. So we could say that the change in length from A to C plus the change in length from C to B has to be equal to 0. And then we expand those two terms out using our equation for axial deformation, which was change in length is NL over AE. So doing that, we get NAC over LAC divided by AE, leaving out the subscripts if they're the same material, and then NCB LCB divided by AE equals 0. Okay, so we've got one equation of statics up here, and then we can see here in the second equation that we're developing that we can cut out the denominator there by multiplying both sides of the equation by 0. And then we can see that we can actually make substitutions for NAC and NCB in terms of AY and BY. For example, if we take our section cut through the object at that location, we can see that we have AY here, and the normal force NAC must be equal to AY. So we can make that substitution, and then that will allow us to build up a second equation with the variables AY and BY in it. Okay, so we've got now NAC is equal to AY, so we've got AY LAC plus, and then we do the same thing over here, take a section cut through that, and we can see that BY is equal to the normal force in CB. Make that substitution, BY, and this is LCB is equal to 0. Okay, and that becomes our second equation there. Now, important to remember when you're doing superposition is to always look at the nature of the normal force and appropriately choose the sign. So we've got a tensile force for NAC, so this is a positive value there, but we've got a compressive force for NCB, so we should have a negative sign in front of BY there. So we've got two equations now, again assuming we knew dimensions and that externally applied load F. We have two equations, two unknowns, we can solve them. So the process of going through and building up a second equation from the deformation constraints placed on an object is known as applying compatibility criteria. So whenever you've got a situation that's statically indeterminate, then look toward deformations to build up a second equation and apply your compatibility criteria. So let's do an example of a statically indeterminate problem now that's a little bit just slightly different from what I've just done. So example, okay, so we're gonna have a steel rod that is attached to a fixed support here, okay, like this. So there's a fixed support, and there's going to be another fixed support over here, but the rod is not going to quite reach to that. So we're going to have a 0.2 millimeter gap here between those, and we'll apply a load that's 20 kilonewtons. Okay, and the distance from the wall to that load is going to be 400 millimeters, and the distance from that point to, let's make that a better line, the distance from that point to the end is going to be 800 millimeters. There we go. Okay, so some information about the rod now. So we've got a steel rod, let's say it's 10 millimeters in diameter and has a modulus of elasticity of 200 gigapascals. And what we want to know is when the 20 kilonewton load is applied, what are the support reactions? Okay, so support reactions when 20 kilonewton load applied is the question. All right, so when the 20 kilonewton load is applied, the portion here of the rod to the left is going to elongate, and if it elongates enough, then this end will contact the wall, and then the wall will begin to start pushing back on that end. So we'll have tension in this section and compression in this section. And the way to go about starting this problem is just by assuming that 20 kilonewton load is sufficient to close that 0.2 millimeter gap, and then draw a free body diagram based on that. So let's say assuming that the gap closes, right, then we have a free body diagram that looks like this here, where we've got our 20 kilonewton load there, and we'd have a x pulling back that way, assuming that this is point A over here. Let's make this point B here, and we'll make this point C where that 20 kilonewton load is applied. And then we've got Bx acting back that way. Okay, so equations of statics, sum of the forces in the x direction has to be equal to 0, right? That way it's positive. We've got minus ax minus bx plus 20,000 equals 0. So we've got ax plus bx equals 20,000. Okay, and that's equation number 1. So statically indeterminate, right? Because we've got one equation, two unknowns, and that's as far as we can go using our equations of statics. We can't solve it. So let's look at creating another equation using compatibility criteria. So we'll say that that the change in length of the object, delta L of AB, in this case, it's not equal to 0 because point B can move, but we know that the total change in length of AB has to be constrained to 0.2 millimeters. So we've got 0.2 times 10 to the minus 3, right? I'm putting this number here in meters, this number here in newtons, so we maintain that meters, newtons, pascals unit convention. Okay. Now, this is going to be a superposition problem where one section between A and C has a certain normal force in that's equal to AX, and the other section has a normal force that will be equal to BX. So we know we have to use superposition here. So delta LAB will be equal to delta AC plus delta LCB equals 0.2 times 10 to the minus 3, and then we expand those two terms out. So NAC LAC over AE, again dropping the subscript because they're the same for both segments, NCB LCB over AE equals 0.2 times 10 to the minus 3. Okay. Now we need to make our substitution there. So let's draw our section cuts. And even though this seems straightforward, it's best to draw those section cuts and draw the internal normal forces so you remind yourself that you should be looking at whether they're tensile or compressive, and also don't make a mistake there. So we just draw the free body diagram of the object again, so we have it handy here. We've got 20 and BX and AX. So we're going to take one section cut through here, and that section cut looks like this, where we've got AX, and then we've got NAC has to be equal to AX, and then our next section cut through that portion to reveal the internal normal force in segment CB. We've got BX, and then we must have a normal force to counteract or to balance that, so that's NCB, and it has to be equal in magnitude to BX. All right, so returning to our previous page here, we'll just grab this line. Okay, copy that, and go back over and paste it in here. Okay, and then we'll continue on the next line. So now we've got NAC. We can see that is equal to AX here, and that the normal force is tensile, so it goes in the equation for NAC as a positive value. So we've got positive AX here. Let me just make that a little bit nicer. We've got positive AX, and then LAC, what was our length there? We had 400 millimeters, so we've got 0.4, and then we'll divide by a common denominator, so we'll do our next term, NCB. So here's NCB over here, it's BX, and note that it's compressive, so we've got minus BX, and then the other segment was 800 millimeters long, and we're dividing by the cross-sectional area. We said that this was 10 millimeters diameter, so pi over 4, 0.01 squared, and then our modulus of elasticity was 200 gigapascals, right there. So we'll put that in 200 times 10 to the 9, and that all equals 0.2 times 10 to the minus 3. So now we've got a second equation, right, with our two variables AX and BX in. So we've applied compatibility criteria and considered deformations to build up a second equation, and now we can plug those both into our calculator and say solving 1 and 2, we get values for AX and BX, and if you do that, AX is 16 kilonewtons and BX is 4 kilonewtons. Okay, there we go. All right, so one important note here is that BX came out to be a positive value. Now, because it came out to be a positive value, that indicates that our assumed direction of BX was correct, which means that the rod actually did close, or that the 20 kilonewton load was sufficient to close that 0.2 millimeter gap. If you had have done this problem and you got minus 4 kilonewtons, let's say, or any negative number for BX, what that physically would mean is that the real direction of BX would need to be reversed, and it would need to be in this direction. And physically, that would mean that the wall would have to have reached out and grabbed a point B and pulled it across, which isn't possible. So a negative sign here would indicate that the assumption that the gap was closed was incorrect. So then you need to step back, and then the problem would be not a statically indeterminate problem anymore, because AX would simply be 20 kilonewtons. Okay, so that is statically indeterminate axial loads. So the next axial deformation topic we're going to look at is thermal elongations and contractions. So thermal elongation and contraction. Okay. Most things, when you increase the temperature, they expand, and when you cool them down, they contract. The notable exception being water, of course, but most engineering materials behave that way. And even though the length changes that things undergo are small in response to temperature when the objects are small, when you have something that's very long, the length change can be very significant when there's a temperature change, and that can induce incredibly high stresses and cause yielding of the material, etc., etc. without doing any proof here, I'm just going to write the equation for how you calculate the length changes due to change in temperature, and then we'll do an example problem looking at that. So the equation for thermal elongation and contraction is delta L subscript T is equal to alpha delta T L. Now, just to explain the different components here, alpha in this equation, alpha is a material property called the coefficient of thermal expansion. Coefficient of thermal expansion. Okay. And you can get this from the material property tables in the textbook, and it has units of degrees to the -1, so 1 over degrees Celsius or 1 over degrees Fahrenheit, depending on what unit system you're working in. Delta T is the change in temperature, so that's the final temperature minus the initial temperature, and L is the length of the object at the initial temperature. So this is length at Ti. Okay. So now you can see that the change in length due to temperature that something undergoes is directly proportional to its original length. So as something gets longer, it will experience a longer or a greater length change due to a given temperature difference. So let's look at an example problem using thermal elongations and contractions. So, example. Okay, so let's say you are designing some of the steel work on a bridge that's being built, and the main structural components of the bridge include these very long steel girders that are, we'll say they're 100 meters long. Okay, and these will be steel girders, and then we'll say that they have a cross section that is the shape of an eye, so they're I-beams. So they've got cross sections like this. We'll talk a lot more about I-beams when we do bending stress. And the cross-sectional area is 246 centimeters squared, we'll say. Okay, now there's a pin here on one side, and long pieces of steel in bridges like this are always allowed to freely move on one end. So sometimes it's a pin and a roller on the other end. Sometimes you have expansion joints with sort of rollers below to allow extension to occur. But let's say, being a young engineer, you forget to put in that roller and you pin that girder at both ends to constrain its length. And let's make up a problem statement. So let's say that steel girder is put in place and the bridge is constructed when the temperature is 25 degrees outside. So bridge built when the temperature was 25 degrees Celsius. And let's say that the design safety factor for this was 3. So the bridge was built using a design safety factor of 3. And the steel that was used is common structural steel with modulus of elasticity, let's say, of 200 gigapascals and a yield strength of 250 megapascals. Now, what we want to know is when the temperature drops on a cold winter day to minus 20 degrees Celsius, is that steel girder safe? Okay, so when temperature is minus 20 degrees Celsius, is the girder safe? Oops. Okay. So the design safety factor was 3, so the girder would not be safe if the stress was large enough so that the safety factor fell below 3. So really what we want to do is we want to figure out what the maximum stress in that girder is, and then compare that to the steel's yield strength and divide it by the safety factor. And what we'll do is we'll calculate that, and we know that, and then we'll figure out what the safety factor is for the situation when the temperature drops to minus 20 degrees Celsius. And if it's smaller than 3, then the girder isn't safe, and if it's larger than 3, then all's good, and we've got a safe design that's maintained. So let's just look at the girder by itself here, and maybe I'll get a new page here. We'll look at the girder by itself, and let's just consider what's happening. So there's the 100-meter long girder. Now, when the temperature drops from 25 degrees Celsius to minus 20 degrees Celsius, that girder is going to want to contract by some distance, delta L subscript T, the length change due to temperature, right? But because the girder is pinned at both ends, it can't actually change length. So it's going to be pulled back to its original length by the tensile normal force that's being imposed by the pin connections on both ends. So we have a situation here where the length change due to temperature plus the length change due to the internal normal force has to be equal to 0. Now let's expand both of those terms out. So we know that length change due to temperature now is alpha delta T L, and the length change due to an internal normal force is NL divided by AE, and that's equal to 0. Now, looking back at the previous page, we know that we want the current stress in the object, and we know that stress is N divided by A. So looking at this next page, that term appears right there, so we can substitute sigma in and then not worry about getting our normal force out of this expression and then having to divide it by the area to calculate stress. We'll just pop that in right now. So we'll change this to alpha delta T L plus sigma L over E equals 0. So this sigma in this equation is the stress that the column or the girder is under when we have that temperature change. So let's go ahead and figure out what that is. So alpha, I didn't write down a value of alpha, but I should have here. So let's put this in the problem statement. So also alpha is 12 times 10 to the minus 6. Per degree Celsius. Okay, that's the value for your typical structural steel. So you'd need that to do the problem. So we've got 12 times 10 to the minus 6 here. Temperature change. We have not minus 45. We've got, I'm getting ahead of myself there. Minus 25 is the final temperature. Subtract the initial temperature, which is 20. Difference is minus 45. Length is the original length of the steel. That's 100 plus our stress, length 100 divided by modulus of elasticity, 200 times 10 to the 9. Okay, so out of this equation, we get a value of stress that is 108 MPa. Okay, so now we can use that expression that we had, which said that the maximum stress that's in the column, which is equal to 108, is going to be equated to the yield strength over the safety factor. So we've got 108 megapascals, right, times 10 to the 6 equals the yield strength 250 megapascals times 10 to the 6 divided by our current safety factor. And the safety factor there, when we do the math, comes out to be 2.3. Okay, so that's less than 3. So according to our design safety factor, this girder is not safe purely by the stress that is caused by that temperature difference. Okay, so we've got, because 2.3 is less than 3, not safe. All right, so that's basically all there is for thermal elongations and contractions. We're not going to do a ton of problems with those, but they're important to know about and to take into account when engineering, because they can cause very, very large stresses. So now we're going to look briefly at the concept of stress concentration. Okay, and this is changing gears a little bit from the axial deformation now, but it's a minor topic that we need to cover at some point, and it slots in here kind of nicely. So what I want you to do is consider two flat plates. So let's draw one here. Try and draw them quite similarly to one another, and another one here. Okay, and in one of these plates, what I'm going to do is put a hole in it like that. And what I want to do is consider how force has to flow through these plates when a load is applied, a tensile load in this case. So when a tensile load is applied, you have an atom and an atom next to it, and this atom is being pulled away from this atom, so there's internal force that's flowing through and between these, so you can sort of draw an internal line of force transmission through your object that's going from one side to the other as atoms transmit that force through the plate from one atom to another. And you could draw lines of force transmission, internal force transmission, through the plate from sort of top to bottom like this. Okay, they should all be nice and straight there. I know they're not in my drawing, but okay, so these are lines of internal force transmission. Okay, so now let's consider how the internal force transmission is affected by this presence of a hole. Okay, so we've got our forces being applied here. Now, if there's a hole in that plate, then the material at this edge doesn't know that there's a hole there. So it's going to transmit force from one to another. But the force can't be transmitted across the hole. So at some point, the fact that the material right here can't transmit any force to its neighbor and is therefore relatively unloaded is going to propagate outwards and cause this line of internal force transmission to need to curve up and around the hole before coming back down like this. And then the line of internal force transmission directly below is going to do the opposite. It's going to have to curve around that hole because force can't be transmitted through the hole. And then that's going to affect the next line a bit as well, like this, and then so on and so forth as we get sufficiently distant to that hole where the line of force transmission is no longer being affected and is going straight across. Now, we know that stress is a measure of average internal force, so the density of these lines of internal force transmission is sort of a proxy for stress. And what you can see is that right at the edge of this hole there, we get a densification of the lines of internal force transmission. And this is what is called a location or an area of stress concentration. So stress concentration occurs here. Okay, stress concentration, right? At this location, the effect of this stress concentrator, which is the hole in the stress concentration that occurs, the effect is that the maximum stress right at the point that's adjacent to the hole, the stress is going to be significantly higher than the stress that you would calculate just by doing your normal force divided by cross-sectional area at that location, calculating your average normal stress. The stress there is going to be significantly greater. So the way that you calculate the stress at this location, so sigma max, is you use what's called a stress concentration factor K, and you just multiply that by the regular stress that you'd calculate the average normal stress. So this is the maximum stress occurring at stress concentrator is given by this equation here, right, where K is called a stress concentration factor. And we get these from stress concentration tables. We get them from tables, right? The values of K don't have anything to do with the material that something's made out of. They just depend on the geometry of the stress concentration feature that you're dealing with. So there'll be a table of K factors for holes in flat plates, for example, or a table of K factors for plates that change width, and how those K factors vary with fillet radius in the plate. And then there's stress concentration factors for torsional situations where you have change in diameter of shafts, et cetera, et cetera. So you go to the appropriate table and look up the value of K. Now, you'll have a point of stress concentration like this whenever you have a change in cross-section to an object. So again, it could be a hole in a plate or an object. It could be a change of width or a change of diameter. Anytime you get a change in cross-section, you have an area of stress concentration. So let's just pop over to the textbook for a second and we'll have a look at what those stress concentration tables look like. So let's see, that's not what I want. There we go. Okay, so here's two stress concentration tables from the textbook. So what you do when you're using these tables is, for example, if we're looking at the the hole in a, let me just bump the width of this up a little bit. If we're looking at a hole in a flat plate like this, then we can see that there's some dimension labels here, the width of the plate, the diameter of the hole. And if you look on the chart, you can see that K values are along the y-axis here. The ratio of hole diameter to width of the plate is down on the y-axis, or on the x-axis, and then there's a line on the graph. So what you do is you calculate this parameter d over w, find where you are on the x-axis, and then wherever you are, let's say you're here, you read up, hit the line, and then read over, and then your K value is the corresponding value on the y-axis. If you've got a plate that changes width, then there's a fillet in here like this, then the chart is a little bit busier with multiple lines. So first you have to calculate the parameter w over h to figure out which line you're on before you continue with reading off your K value and finding where you are on the x-axis. Okay, so that's the tables there. Let's flip back to the lecture notes here. Okay, so let's do one example with stress concentrations. They're pretty basic things. So example. Okay, so let's say that we have a flat plate here that looks like this. We've got a fillet down to a smaller portion here. Okay, there we go. And let's bump this out into 3D. Okay, there we go. Okay, and let's put a hole in here, and what we'd see this side, something like that. And let's say that this is experiencing a tensile axial load of 8 kilonewtons there, 8 kilonewtons on that side as well. And some dimensions would be good. So we've got, let's say, 30 millimeters for the width of the small portion, and then 60 millimeters for this portion, and our hole diameter we'll make that 12 millimeters, and the radius here of our fillet we'll say is 15 millimeters, and the thickness of the plate is 5 millimeters. Obviously not drawn to great scale here. So the question is, we just want to know what the maximum stress in this plate is. So there's two locations of stress concentration that we need to consider. First of all, we know that at the top and the bottom of this hole is going to be a location of stress concentration. And then for a fillet like this, where you've got a change in width of a plate, the location of greatest stress concentration is on the smaller width portion, just at the start of the fillet. And the sharper that transition is from small width to large width, so the smaller the radius of the fillet, the greater the stress concentration will be. As you get a larger radius fillet, and that transition from large width to small width happens over a longer distance, is more gradual, then the magnitude of the stress concentration will go down and down. So let's deal with the hole first. Okay, so I'm going to pop back to the book, and we'll see what we need to do for the stress concentration factor for the hole. So for a hole, again, what we need is on the x-axis, we need d over w, where d is the diameter of the hole, and W is the width of the plate. So we'll go back and do that. So we've got D over W is 12 over 60, which gives us 0.2. So now we can say from chart K equals, so 0.2, so we'll flip back here. There's 0.2, so we go up, and we go over. So this is 2.4, 2.5, 2.6, so this would be 2.45 about. So we'll go back here, 2.45. Okay, so now we can say that for the hole, the maximum stress at those blue dots that I've drawn will be equal to our K value multiplied by the normal, average normal stress that we would have calculated. So this is 2.45 multiplied, and this would be K, and then N divided by A here. So we've got 2.45 multiplied by the internal normal force. Now, if we did a section cut through the location of the hole here, we get a free body diagram that looked, let's draw it in 2D, looked like this, where we've got 8 here and a total internal normal force of 4 on sort of one side of the hole, 4 on the other side, so the total internal normal force is 8 there. Okay, so let's just draw a free body diagram for what that would look like if we... So let's just draw a free body diagram for what that would look like if we did section through the hole, just in 2 dimensions there. So we've got 8 there, and we'd have 8 kilonewtons on the other side as well. So we've got our 8,000 newtons here, and then for a cross-sectional area, we have the width of the plate, which would be 60 millimeters minus 12 millimeters, and multiplied by the thickness, 0.005 millimeters. Okay, and that is going to come out to give us 81.7 MPa. Okay. Now, we don't know if that's the actual, we know that that's the maximum stress adjacent to the hole, but we don't know if that's the maximum stress in the plate yet, because we still have to do the same thing for the fillet. So let's say that for the fillet, flip back to the book to see what parameters we need. So we need, first of all, to figure out which line we're on, we need W over H, where W is the width of the large portion, H is the width of the small portion. So W over H here is what? The large portion over the small portion is 60 over 30. So we've got 2 there. And then the other parameter that we need on the x-axis is R over H, and that's the radius of the fillet over the width of the small portion. Okay, so R over H. Radius of the fillet was 15 millimeters and small portion is 30. So we've got 15 over 30 gives us 0.5. Okay, so we take these 2 values and we return back to our book over here. So we're on 0.5 on the x-axis. So there we are, and we go up until we hit the line for 2. So we've got a line for 1.5, that's this line. We've got a line for 3 that's that line, so the line for 2 is somewhere in between there, so it looks like we're approximately at 1.4. So this means that k is 1.4. Okay, and again we say sigma max equals our k value multiplied by our regular normal stress, our average normal stress that we'd calculate, k multiplied by n divided by a. So we can do the math on that. 1.4, 8,000. Okay, and then our cross-sectional area here is this cross-sectional area right there, which is 30 millimeters by 5 millimeters. Oops. 0.03, 0.005, and that gives us what? 74.7 megapascals. Okay, so therefore the actual maximum stress in the plate is the stress adjacent to the hole, which was 81.7 megapascals. Okay, so now that you sort of know about stress concentrations and how to deal with them mathematically, now is when I get to tell you that we won't be considering stress concentrations for the rest of the course. And that's for a good reason. Stress concentrations are super important when you're dealing with brittle materials, because in a brittle material, when a crack, when stress is exceeded, there's only the ultimate stress. So that results in a crack forming, and cracks in brittle materials propagate very easily and rapidly through the material. But in a ductile material, if you, for instance, exceeded the yield stress of the material right at this location adjacent to the hole, if you exceeded your yield stress, then you'd get a bit of plastic deformation at that location. But we know that the stress strain curve for ductile materials, we have the yield point and then we have a further increase in strength. So what we're going to do is just go past the yield point a little bit, and then the material will actually start becoming stronger there. So we won't have overall failure of our component if we exceed the stress in a very specific location due to a stress concentrator. So for that reason, when we're designing objects and structures using ductile materials, we often ignore stress concentrations because they're just really not that critically important and don't affect the structural integrity of objects a great deal. Okay, so that brings us to the end of this lecture. I'll see you again for lecture 5.